Today, on How It's Made. Car engines. Checking out what's under the hood. Flour. A product that's really put through the mill. Recliners. Furniture you can sit back and enjoy. And envelopes. They take a licking and keep on sticking. Car engines work by internal combustion, a process that happens in each of the engine cylinders. Air and a drop of gasoline enter the cylinder. The piston moves upward, compressing the mixture. The spark plug ignites the gasoline, causing an explosion that drives the piston downward, powering the engine. Engine components are housed in what's called the engine block. It arrives at this plant partially made. Here they finish it off by machining the cylinder bores, the holes in which the pistons move up and down. The tool carves a crisscross pattern on the cylinder bore walls. Lubricating oil will cling to the grooves in this pattern, enabling the pistons to move smoothly. After machining, the engine block travels upside down to the engine assembly line. When it arrives there, a scanner records the block's traceability code, a barcode that enables the factory to track the block through every stage of production. As the engine block travels down the line, error-proofing devices ensure that each component is installed properly. Elsewhere in the factory, meanwhile, the crankshaft is slowly taking shape. The crankshaft is a bar that's rotated by the up and down motion of the pistons. As it turns, it transfers power to the transmission. The crankshaft starts out as a roughly shaped steel forging. Robotic arms pass it down the line from station to station until, 20 tooling machines later, it's fully formed. They install a steel disc with teeth called the reluctor ring. They heat it and press it onto the crankshaft. As it cools, it shrinks to a tight fit. This ring helps time the combustion cycle. As it spins, its teeth pass in front of a sensor which reads the crankshaft's position and tells the engine to fire the spark plugs at precisely the right moment. Now they balance the crankshaft. If it's off kilter, the engine will vibrate. A computer analyzes the spin and determines whether they need to drill out metal at certain points to achieve equilibrium. Back on the engine assembly line, the engine blocks are still upside down. A robot lubricates the 4 bearings on which the crankshaft will turn. Then it drops the crankshaft into position. The pistons come next, 6 per engine, because these are 6-cylinder engines. The pistons are made of aluminum. Robots install them into the cylinder bores of the engine block. A steel connecting rod attaches each piston to the crankshaft. Now workers can close up the back of the engine block. A robot applies sealant to the rear cover. They bolt it on manually with a tool called a multi-spindle torque gun. On another line, they assemble the 2 heads that'll cover the top of the engine block. This robot is applying sealant to spark plug tubes before inserting them into the heads. The heads cap off the cylinder bores. They provide each cylinder with a spark plug and 4 valves, 2 for allowing the fuel mixture in and 2 for releasing the exhaust. The black tubes running front to back are the camshafts, the components that open and close those valves. There are 4 per engine. A robot applies sealant and then bolts a cover onto the front of the engine block, the head, and a component called the timing chain. This chain connects the crankshaft to the camshafts so that they rotate in unison. This ensures the valves open when the pistons are in the right position. Finally, they spin the engine mechanically to make sure the components function properly. The grain most commonly ground into flour is wheat. Flour mills use high-protein or hard wheat species to make bread flour, and lower-protein or soft wheat species to produce cake and pastry flour. All-purpose flour is a compromise with medium protein. As soon as the wheat shipment arrives, a grain probe vacuums up samples from throughout the load. If the samples pass quality inspection, the mill gives the truck the go-ahead to dump the wheat to an underground conveyor. From there, the grain goes into a cleaning machine where a system of sieves removes impurities such as straws, sticks, and grain dust. The wheat then goes into storage silos until milling time. The protein content of wheat varies by species, so the first step is to blend together the right varieties of wheat for the type of flour they'll be making. From the blender, the wheat goes through a second, more intensive cleaning system that removes the tiniest of impurities, such as weed seeds and dust. On the way to the milling machines, a scale tracks production quantities. This mill's vertical production line is 5 stories high. Gravity carries the wheat downward through a succession of milling machines. Each one grinds the grain between steel rollers, then sifts it. Particles too large to pass through a sieve continue downward into the next milling machine, and so on. By the last machine, whatever's still not fully processed gets vacuumed up to the top to begin the cycle again. Mills make white flour by grinding only the wheat kernel's soft inner part, called the endosperm. This requires removing the bran, the kernel's hard skin, and the germ, its seed. That separation begins as soon as the wheat kernels enter the very first milling machine. Rollers break off the germ and bran and crush the endosperm into pieces called semolina. Sifting removes the germ and loose bran pieces, but much of the semolina remains covered in bran particles. So between each milling station is a purifier, a machine that uses controlled air currents to float the lighter bran above the heavier semolina, enabling sieves to separate the two components. The semolina goes through repeated grind, sift, and purify cycles until it's completely clean. Only then can it be finely ground into flour. The ground semolina passes through a series of sieves. This ensures it doesn't leave the final milling machine until it's been ground to just the right powdery texture. There are 3 main types of white wheat flour. Bread flour has high protein, enabling dough to rise well and bake to a firm texture. Cake flour has low protein, which produces a crumbly texture. All-purpose flour is the compromise. Its medium protein content makes it suitable for baking both bread and cakes. By the end of production, the flour mill has produced 3 distinct products: bran, used for animal feed and baking; white wheat flour, of course; and wheat germ for the health food market. Leftover byproducts go into livestock feed. In the mill's quality control lab, they bake the product for which the flour is designed, then examine its appearance, texture, and taste. They use specialized equipment to calculate the volume, the density, the protein, and moisture contents. With baked goods destined for retail sale, like these cookies, it's especially important to measure the dimensions. If the dough overexpands, the cookies won't fit in their package. Just prior to packaging, the mill enriches its white flour with vitamins and minerals. This replaces the vitamins and minerals lost when the milling process removed the bran and germ. They shake the bags to settle the flour. Bagged flour in various sizes goes out to supermarkets, restaurants, and commercial bakeries, while tanker trucks ship bulk flour to large industrial bakeries. The first reclining armchair was introduced by the La-Z-Boy Company in 1928. Today, many companies make motion furniture, as the industry calls it, and the term recliner no longer refers to just armchairs. You can buy reclining couches and even reclining sectionals. This factory makes reclining chairs and couches in both fabric and leather. The furniture construction is the same regardless of the material. However, leather upholstering requires a few extra steps. They begin by inspecting the hide, marking serious defects with one color of tape and minor imperfections with another. A computer-programmed cutting machine scans and registers the tape markings, then automatically cuts and discards the defective parts. It cuts upholstery pieces for hidden areas, such as the undersides of seat cushions, from the imperfect leather, and visible parts from the flawless leather. Once all the pieces are cut, they sew together the back, seat, and arms. Then they stuff the arms and back. They position the open end against a blowing machine that fills it with polyester fiber. Workers weigh each part before and after filling. This ensures they've blown in the right amount of fiber and also that both arms have equal filling. Next, they'll fill the seat with foam. A compression machine squeezes it, then a worker sprays on silicone lubricant. This enables the seat cover to slide on easily. Foam is made of a chemical mixture, the formulation of which determines the density. The higher the density, the higher the quality. Elsewhere in the factory, meanwhile, they cut the frame components from plywood using a computer-guided bandsaw. These long pieces will form the seat frame. A three-seater couch has three separate frames, enabling each seat to recline individually. A machine lines one side of each piece with steel spring clips. A worker then dabs the ends in glue and assembles the pieces, reinforcing them with long glue-coated staples. As the staples enter the wood, friction-generated heat melts the glue. The glue then dries, securing the staples. Now comes the step known as springing the seat. They hook 5 thick steel springs into the spring clips, then hammer the clips closed to lock the springs in place. They connect the springs with a plastic-covered wire so that when you sit on the seat, all the springs react in unison. They assemble the frame pieces for the arm using glue and glue-coated staples again, plus a few screws at strategic points. They screw the arm to the seat and begin upholstering. First, a layer of felt to cushion the springs, then wood, cardboard, and foam to form the rounded shape of the armrest. After lubricating with silicone spray, they slip on the leather and staple it into place. They upholster the backrest and sides in the same manner. The reclining mechanism arrives at the factory with the sides pre-assembled. Workers install the connecting pieces, then a bushing that reduces the noise the mechanism makes, then a spring to control the recline speed. They screw the mechanism to the seat frame, then hook up the operating handle and test it out. To cover the back of the furniture, they attach metal tacking strips to the leather, then turn the edge under and hammer the tacks into the frame using a pneumatic hammer. The last step is to attach the back to the seat. There's a detachable flap at the bottom, providing access to a locking spring inside that lets you remove the back if you have trouble getting the furniture through a doorway. At this factory, workers are encouraged to lie down on the job, but only to inspect the furniture. After examining the fabric and sewing, they assess the comfort and test the reclining motion. Talk about a cushy job. We rip it open with barely a thought, more anxious to read its contents than to take a moment to truly appreciate its form and function. And then we ruthlessly discard it. The humble envelope just doesn't get much respect, despite its distinguished 4,000-year history. As early as 2000 BC, the Babylonians baked special clay wrappers to transport documents. Eventually, people made envelopes from lighter materials, such as animal skins and leaves. By about 1000 AD, it became the custom to simply fold a letter and seal it with a drop of wax. But everything changed in 1837 with England's new penny postage system. To mail a letter, the sender now had to buy a postage-paid paper wrapper that folded into an envelope. One of the many envelope styles this factory makes is a 30 by 46 centimeter envelope made of natural color craft paper. A machine appropriately called the sheeter cuts the roll into 53 by 63 centimeter sheets. A worker selects the cutting die for this style and installs it on an automated press. As each stack of sheets passes underneath, the press applies 10 tons of pressure, forcing the die right through like a giant cookie cutter. The shaped sheets are called envelope blanks. Workers now load the blanks into the feeder of an automated piece of equipment called a blank sheet envelope folding machine. As we see here in slow motion, revolving steel blades first make score lines, 4 in all. 1 down each side, creating the envelope side flaps, 1 across the top, creating the seal flap, and 1 across the lower end, creating the bottom flap. Folding blades hold the paper down along the score lines, while arms push up from underneath, folding the side flaps toward the center. Just before the flaps meet, the machine runs a line of glue down their edge. The flaps adhere to each other, forming the center seam that runs down the back of the envelope. The machine then glues the bottom flap and folds it closed. You can see in slow motion how it also applies glue to the seal flap at the top, keeping that flap open so that the glue will dry. The sender has to just remoisten the glue to seal the envelope. The finished envelopes exit the folding machine and enter another machine that counts them and stacks them upright. This more sophisticated piece of equipment is called a web roll envelope folding machine. They feed the roll of paper directly into the machine, and as we see here in slow motion, it does everything from cutting, scoring, folding, and gluing the blanks to counting the finished envelopes. For this style, a die even punches out an address window in the front of the envelope. This all-in-one machine goes through all the steps at lightning speed, 20 envelopes per second. The thin, transparent film that covers the address window is usually made of polypropylene. The machine cuts it to size and glues it to the envelope. This machine doesn't have folding blades to hold the paper down along the score lines. Instead, the blanks roll through a series of rotating cylinders with air holes. A suction system vacuums the blank to the cylinder while the operation is being performed, then releases the vacuum to transfer the paper to the next cylinder, where it's vacuumed on for the duration of the next operation. Internal mail envelopes are opened and closed repeatedly, so they don't have a lick-and-stick seal flap like regular envelopes do. As we see here in slow motion, an automated machine rivets a cardboard button to the back of the envelope. At the same time, it rivets another button with a piece of string to the flap. Envelope factories use many different types of paper, from top-quality vellum to craft paper. With printing equipment incorporated right into the folding machines, they can print return addresses, even elaborate custom designs. Today on How It's Made. Conga drums. Handmade and hand-played. Metal plating. We'll uncover the process layer by layer. And buttons, a special two-part report guaranteed to be fascinating. The conga drum may be a staple of Latin American music, but it developed from an ancient African drum, made from an animal skin stretched over a hollow tree trunk. Today, they stretch the hide over a wood or fiberglass cylinder. As you're about to see, making congas takes plenty of hands-on skill. These congas are made of ash, a wood that has good acoustics. That means sound resonates off it rather than being absorbed into it. First, the drum maker cuts the curved slats that will form the drum's body, called the shell. He traces a slat-shaped template on a rectangular piece of wood. Then, using a bandsaw, he cuts along the trace line, creating a curve on the outside and inside surfaces. Then he moves to a bench saw, a saw whose blade can be adjusted to different angles. He clamps the piece onto a template and angles the edge. He flips the piece over and angles the other edge. The drum maker applies carpenter's glue to both edges and clamps the slats together in a circle on a specially designed form. The number of slats per drum varies depending on the diameter of the shell. The larger the diameter, the lower the congas sound. The glue dries in 24 hours. It comes off the form looking like this bongo shell, but taller. The drum maker now mounts the dried shell on a wood lathe. Using a tool called a wood gouge, he shears off about 6 millimeters, rounding the outside of the shell. Then he uses a series of woodworking tools to add decorative detailing. Once that's done, he smooths the shell's surface using 3 progressively finer grains of sandpaper. Then he either leaves the wood its natural color or stains it. A thick coat of oil-based lacquer protects the wood from both dryness and humidity. Now for the essential hardware. First, side plates made of chrome-plated steel. Their job is to anchor the drum's animal skin head. They're bolted to the shell. Next, the drum maker feeds a steel strip through a bending machine. Its high-pressure rollers curve the strip, forming the drum's rim. Then he rivets V-shaped steel pieces onto the rim. Elsewhere in the workshop, they prepare the cowhide that will become the drum's head. First, they soak it in a corrosive bath of cold water and lime. This literally burns the hair off the hide. After 2 or 3 days, they remove the skin and scrape off any stubborn hairs. Then they stretch it over a circular frame, leaving it to dry at room temperature for a couple of days. After chrome plating the rim, it's time for the final assembly. They stretch the head over the shell and clasp it in place with the rim. They hook the V's to the side plates, then adjust the tension to tune the instrument. The last step is to trim off the excess skin. Now, the musical handiwork can begin. Plating is a layer of metal coating an object of a different type of metal. The purpose can be decorative, as in silver plating, or practical. With industrial parts, for instance, zinc or cadmium plating prevents the underlying metal from rusting, while nickel or chrome plating protects against wear. You can plate almost any type of metal. Let's follow some steel aerospace parts as they're about to be plated with cadmium to make them corrosion resistant. For the plating metal to bond properly, the steel surface must be free of contaminants such as oil and grease. Workers suspend the parts over a vat of boiling chemical solvents. As the hot vapor comes into contact with the colder metal, it condenses, dripping down into the vat and taking any contaminants along with it. The remaining solvent residues evaporate, leaving the parts squeaky clean and dry. Next, a worker wearing protective clothing sandblasts the parts with aluminum oxide powder, a strong abrasive. This roughens up the surface so that the plating metal will adhere better. The most common plating metals for industrial purposes are zinc, chrome, and nickel. Think motorcycle parts or sink faucets. Decorative items, on the other hand, are more likely to be plated in tin, brass, gold, or silver. Traditional tea sets, for instance, are often made of silver-plated copper or zinc. The plating process is called electroplating because the key to it all is electricity. They start by tying strands of copper wire to a copper support frame, copper being the best metal for conducting electricity. Then they attach the steel parts they'll be plating. When they hook up this support to an electric current, electricity will run from the support through these wires right to the pieces. They do the electroplating in a tank. After filling it with water, they add a handful of chemicals to help conduct electricity, because water alone won't conduct it sufficiently. Along the sides of the tank, in bags, are metal baskets. They contain bars or balls of the plating metal, in this case cadmium. Workers connect the support frame with the steel parts to the negative terminal of an electric source, the baskets of cadmium to the positive terminal. Then they switch on a steady DC current, no stronger than 6 volts. The electricity dissolves the cadmium, lacing the particles with a positive charge. They travel through the water and attach themselves to the negative charged steel parts, creating a smooth and even layer of cadmium. Thin plating requires just a few minutes in the tank, thick plating several hours. Then workers rinse the parts in water for about a minute to remove the chemical residues. To make the parts even more rust-resistant, workers immerse them in a series of compounds. This triggers a chemical reaction in the plating, enhancing its ability to withstand corrosion. This reaction, however, changes the color. A final rinse in hot water, and this cadmium-plated steel aerospace part is finally ready. From start to finish, the process has taken about 90 minutes. To plate with chrome or gold, they have to use a chemical compound containing gold or chromium. That's because electricity can't dissolve solid chromium well enough, and it can't dissolve solid gold at all. The compound dissolves in the bath like salt, but then solidifies once it reaches the object being plated. Metal plating is very durable, but if subjected to a lot of wear and tear, the object will eventually have to be replated. Have you ever wondered why men's buttons are traditionally on the right side of a garment and women's on the left? Legend has it that this enabled a man to unbutton his coat with his left hand while drawing a sword with his right. Wealthy women, meanwhile, had their buttons sewn on the left side to make it easier for their right-handed maids to dress them. One way to make plastic buttons uses a multi-layer sheet of synthetic resin, hence the industry term sheet buttons. Workers start by mixing liquid polyester resin with a catalyst to gel it. They pour the material into a revolving drum, which disperses it evenly. They spray a solution containing an ultraviolet pigment on this first layer only. You'll see why later on. For this particular model, they make grooves in the resin while it's still malleable. This will create a design. After about 5 minutes, the resin gels, and they can mix and add a second layer in a different color. Besides building up the thickness of the sheet, the resin flows into the first layer's grooves, creating a design of contrasting lines. Once this second layer gels, they mix and pour in a third color. The drum spins for another 10 to 15 minutes until all the layers cure. A resin sheet can be comprised of up to 4 different color layers. Workers can now remove the sheet. It's hardened enough to be cut into buttons, but it's still flexible enough not to crack when cut. Now they feed each sheet into a press that's outfitted with a die for that particular button model. The press punches out circles in the diameter of the button. These circles are called blanks. You can see the different color layers. The blanks move on to the machining center, where they'll be transformed into buttons. Automated equipment loads them onto carousels, the back of the blank facing outward. How does the loader know which side is which? Well, remember that ultraviolet solution the worker sprayed onto just the first layer of resin? A UV detector scans each blank to make sure that first layer is facing upward. If it isn't, the machine rejects the blank, then flips and reloads it. The carousels first run the back of the blank against a series of cutting heads. The heads are changed according to the model being produced. For this one, the heads gradually carve a curved back. The equipment then transfers the blank onto a second carousel, exposing the front side this time. Again, a series of cutting heads gradually carve the front of the button. The shape of this model exposes the different color layers underneath, creating a veined effect. The last cutting head drills the holes. Here you can see the full progression from blank to button. Now they polish the buttons for several hours in drums containing abrasive ceramic stones and pumice. Then workers flush the drums with water. The heavy polishing stones sink to the bottom. The lightweight buttons float to the surface and spill out. The buttons then go into drums that contain silicone wax and thousands of tiny wooden pegs. While the drums spin, the pegs act as a carrier, distributing an even coat of wax. As the buttons exit the drums, the pegs are screened out. From here, plain buttons are often custom dyed to match fabric swatches provided by clothing manufacturers. Well, you've seen how they manufacture some types of buttons, just a few of the many styles on the market. There are several different ways to produce these handy little fasteners, so forgive us if we buttonhole you to stay tuned and watch some more. Archaeologists have unearthed bone buttons dating back to prehistoric times. The ancient Greeks and Romans used buttons to both fasten and decorate their clothing. Europeans wore buttons strictly for adornment until about the 1200s. That's when fitted garments became the trend, fastened by a long row of buttons down the front. The rich wore buttons made of silver or gold, sometimes set with precious gemstones. Ordinary people wore buttons made of mere bronze or wood. This is another way to make plastic buttons using polyester resin. Only instead of turning it into sheets, they pour the resin into long metal tubes. Here they're mixing two different colors to create a design in the plastic. The tubes go into an oven where they bake at 100 degrees Celsius for about an hour until the liquid resin hardens. Once the tubes cool off, workers remove the contents. These long resin rods will become what the industry calls rod buttons. The rods go into a machine called the slicer. Its sharp carbide blade chops the long rods into button-sized blanks. Here's what that looks like in slow motion. It's no use showing you this at regular speed. It would be but a blur. This machine cuts up to 700 blanks per minute. Blanks cut from resin rods run through the same machining center as those cut from resin sheets. In the last segment, we showed you the machining steps in slow motion. Here's what they look like at actual speed. Any type of button can be engraved with a company name or logo. They do this using a computer-programmed laser machine. The laser beam burns the lettering into the plastic. Workers visually inspect the finished buttons to make sure that none have defects. Another way to make plastic buttons is by what's called thermoset compression, a technique that combines both heat and pressure to mold the button's shape. As we see here in slow motion, the raw material isn't liquid resin, but rather melamine powder. A pill-making machine, the kind pharmaceutical companies use, compresses the powder into pill-shaped blanks. Here's what that pill-making action looks like at actual speed. To transform these pills into buttons, workers load them onto a press. The press uses high pressure to force each pill into a button mold for a period of 40 seconds to a minute, depending on the size of the button. At the same time, it heats the mold to 163 degrees Celsius. This bakes the melamine into hard plastic. They cool the molded buttons in a basin of cold water. Some specialty buttons go on to be gold-plated, but not before soaking in a chemical bath to clean their surface so that the plating will bond well. As a rule, only materials that conduct electricity can be metal-plated. Plastic, of course, is non-conductive. However, this company has managed to devise a way to gold-plate plastic buttons. Exactly how is a closely guarded secret it's not willing to divulge. After plating the buttons in copper, a 12-hour process, they plate them in nickel, which takes just a couple of minutes, and finally in 24-karat gold, which takes just a few seconds. A mere 28 grams of gold is enough to plate 82 kilograms of buttons. Thermoset compression buttons are a lower-end product used primarily for uniforms. Sheet buttons and rod buttons are higher quality, the standard choice for fashion clothing. If you have any comments about the show, or if you'd like to suggest topics for future shows, drop us a line at www.howitismade.com. Winter jackets, animation, mushrooms, and gold rings. As anyone who's shivered through a Canadian winter knows, you've got your run-of-the-mill winter jackets, and then those really warm winter jackets that can run you up to $1,000. The difference is what they're made of and how they're made. A top-of-the-line winter jacket gives you the warmth without the weight. It's waterproof and comfortable. No bulky stuffing or constrictive styling. The designer draws a pattern by computer. A software program then adapts the pattern to different sizes. A giant printer puts it to paper. The tailor spreads out several layers of each of the fabrics that'll make up the jacket. He lays out the pattern, then pins it in place. Next, he cuts through several layers of fabric at a time with electric scissors. These scissors maneuver much like a jigsaw around the lines and curves of the pattern pieces. The finished jacket will actually be made up of two jackets sewn together, an insulation jacket on the inside and a windbreaker on the outside. The inner insulation jacket begins with a nylon lining. Then they layer the key components, a film to stabilize and protect the insulation, then the thick polyester insulation itself. At this point, the insulation layer is larger than the lining. This ensures that every inch of the jacket will have insulation. Working with one piece at a time, they stitch the layers together. Each line of stitching is tacked at the beginning and at the end for added strength. They cut off the excess insulation, then sew an overlock around each piece to hold the remaining insulation solidly in place. Once they've completed each piece of the insulation jacket, they sew it all together. Next step, the windbreaker. The outer fabric is heavy nylon. The lining is a special fabric with tiny holes large enough to let humidity escape, but small enough to stop water droplets and wind from penetrating. This is what will allow the jacket to breathe, while at the same time making it windproof and waterproof. Finally, it's time to put the two jacket components together. Using two separate strong threads, they sew seams made of knotted stitches. No seams go through the jacket because that would break the insulation barrier and let in cold air. They join the two jackets together only where they have to, at the collar, the cuffs, the hem, and along the zipper. And this isn't just any ordinary zipper. It's made of corrosion-resistant nylon with a nickel-plated slider that lasts 7 times longer than a normal slider. Until now, they've been sewing the jacket turned inside out. Now they turn it right side in for finishing. These heavy-duty snaps have sturdy grips that anchor themselves between the fibers in the material, so they won't tear the fabric with repeated use. Some jackets have decorative embroidery. Designers use a computer program to prepare the pattern. The automatic machine embroiders 5 jackets at once. This intricate owl pattern takes 1¼ hours to complete. The final result is a stylish jacket whose secret weapon is that hidden layer of insulation. It traps air inside. Your body then heats it up, creating a cushion of warmth against the cold of winter. What is biophotonics? Well, bio is short for biology. Photonics is the physics of light. Biophotonics uses sophisticated imaging and other sensitive optical instruments to conduct biomedical research. Biophotonics has a range of uses, from medical diagnosis to drug screening. In the golden years of animated film, teams of animators would draw every single illustration by hand. Today, they do much of their work by computer, but that doesn't mean it's any less artistic. It all starts with a screenplay, a script containing not just dialogue, but also physical descriptions of the characters and background scenery. The art director begins creating the characters. He draws in pencil. When he's finished, he traces the drawing in felt pen. Then he erases the pencil marks. He adds shadowing to create relief. Once he's drawn all the characters, he starts the backgrounds. And then the objects that appear in the backgrounds. The storyboard artist blocks out the film on paper, drawing by drawing. The production team will follow this storyboard the way a dressmaker follows a pattern. They blow up the drawings, scan them into the computer, then play them back in chronological order. This creates what's called an animatic, a two-dimensional version of the film minus the animation. Should the director now decide to change, say, a ground-level view of the street to an aerial view, he has the artist redraw the street from that new angle. Meanwhile, the animators work on bringing the characters to life. Using specialized software, they build a skeleton to fit inside the character's body. When they move the skeleton, the software makes the body move with it. They make the characters three-dimensional using a technique called wireframe animation. First, they build the shape of the character using a wire structure. Then they add color and clothing. They further refine the character by modifying facial features, by adding texture, and by shadowing. They use specialized software to synchronize the character's mouth with the dialogue. The technician works syllable by syllable, picking the mouth movement that matches each sound. It's a painstaking process that takes many months. Another animator applies the lighting effects. Lighting is as important in an animated cartoon as it is in a movie with real people. It creates relief, making everything look more realistic. The animators cut and paste the characters and objects onto the backgrounds. With the characters' movements programmed into the computer, the animators turn the two-dimensional stills version of the film into a three-dimensional animation, essentially a rough cut of the film. Meanwhile, in the studio, the soundtrack takes shape. Actors record the characters' dialogue. The sound technician weaves together the voices, the music, and the sound effects using specially designed software. They sync the soundtrack to the rough cut of the film. Then they refine the rough cut, playing with colors and textures and smoothing out the characters' movements. After a full year's work and more than 42,000 drawings, this 24-minute computer-animated film is finally finished. Have you ever dined on fungus? Well, if you've eaten mushrooms, you have. We like to think of those tasty little umbrella-shaped things as vegetables, but technically, they're fungi. Fungus omelet, anyone? Mushrooms grow in compost, and preparing that compost is a science in itself. It starts with horse manure and straw. The correct balance of moisture and air is critical because mushrooms need both to grow. So mushroom farmers have to turn the pile frequently to air it out, and they water it daily for about a week. This kicks off plenty of chemical and biological activity. Ammonia forms and microorganisms grow and reproduce, releasing heat. Good compost requires a nitrogen content of about 2%, so farmers add a nitrogen supplement, chicken manure. They also add gypsum, a mineral that improves the structure of the compost and neutralizes its acidity. At the week to 2 week mark, depending on how the compost is progressing, it goes into the composter, which waters, aerates, and blends it. The compost comes out chocolate brown, smelling of ammonia. Next, they pasteurize it to kill off any insects or insect eggs. They heat the compost at 58 degrees Celsius for 8 hours, then at 45 degrees for 5 days. Then, over several more days, they gradually cool it to 25 degrees as microorganisms turn the ammonia into a nitrogen protein, a mushroom nutrient. The compost is finally ready. The farmer sows grains of wheat inoculated with mushroom mycelium, fine threads of fungi that act as the mushroom's roots. A layer of soil and peat moss goes on top of the compost. The mycelium draws water from the soil and nutrients from the compost. After about 2 weeks, tiny mushrooms begin to develop. They grow fast, doubling their size every 24 hours. And this in relative darkness. Green plants need sunlight for photosynthesis, but mushrooms don't. What mushrooms do need is air, because they breathe in oxygen and breathe out carbon dioxide. Green plants do the opposite. Another 3 days and the tiny mushrooms are fully grown and ready for harvesting. Pickers have to be careful not to remove the roots, because left intact they'll sprout a new batch of mushrooms every 3 to 5 days for about 3 weeks. They put the harvested mushrooms in a refrigerator just above freezing temperature for about a half hour to stop the growing process. On the packaging line, they weigh the mushrooms and arrange them in a container, buttons up. A machine perforates the plastic covering to let the mushrooms breathe. This ensures a longer shelf life. The mushrooms stay in a fridge until they leave for the store the following day. It's taken about 12 weeks from the start of composting to your supermarket shelf. Gold jewelry has been a symbol of wealth and status throughout the ages. Today, though, it isn't just for the rich. Even ordinary people are likely to have a gold ring or necklace, just a little less diamond-studded. As early as 2000 BC, Egyptian kings and queens adorned themselves in golden jewelry encrusted with precious gems. When the Spanish sailed to the New World in 1492, they discovered Mayan and Aztec masterpieces of colored stones and pure gold. Today, elaborate gold jewelry and precious gems are well beyond the reach of the average person, except for the diamond ring, still the customary symbol of engagement. The client and the jewelry designer first decide how the ring will look. The designer then measures the client's finger to determine her ring size. He then sketches out the design they've agreed upon, a grooved band with 3 diamonds. The model maker works with a special carving wax. Using a compass, he measures off and marks the width of the band, then carefully saws it off. He takes his millimeter gauge and puts it on a stick with ring size markings called a mandrel. He adjusts his compass to the ring size, then scores the finger hole on the block of wax. He then takes his drill and carefully carves out the hole he scored. Then he grinds off the wax on the outside of the band. Using the compass again, he scores the middle of the band where he'll make the groove. Then, using a very fine drill bit, he carves out the groove. With a file, he then refines the groove and shapes the curves of the ring according to the design. After putting wax prongs on the band, he attaches a wax stem to the model. He then positions the stem into the base of the cylinder that the jeweler will use to cast the ring. The base goes onto the platform of a vacuum machine. The jeweler puts a cylinder on top of the base, then pours in a special plaster. The vacuum sucks all the air out of the plaster. This is a key part of the process because if any air bubbles remain, the finished ring will be out of shape. In less than a minute, the vacuuming is done, and the cylinder goes into the furnace at 1,350 degrees Fahrenheit. The wax model evaporates, leaving a void the exact shape of the ring in the hardened plaster. Next, they melt the gold. The gold content of jewelry is measured by carat. The lower the carat, the less gold and the more alloy, cheaper metals such as nickel, silver, and copper. After 5 hours, the cylinder comes out of the furnace and goes into the casting machine. The machine spins for about a minute. The centrifugal force shoots the liquefied gold into the plaster mold that's inside the cylinder. The jeweler then immerses the cylinder in cold water. This cools the gold and makes the plaster disintegrate. What's left is the cast gold ring, but its surface is rough, so on to the finishing process. The jeweler saws off the stem and gets to work. He files and grinds the ring until the surface is smooth. Then he stamps on his trademark and the carat marking. Then he hammers the ring on the mandrel to make it perfectly round. The jeweler then hands off to a specialist in polishing. The polisher runs the ring against a series of buffing wheels until it's bright and shiny. The polisher then hands off to a specialist in setting gemstones. The setter straightens the prongs that'll hold the diamonds. Then, with a delicate drill bit, he carefully carves out the inside of the prongs. The edges of the diamonds will fit directly into these slots. He readjusts the prongs, then sets the diamonds, making sure the prongs hold them down securely. That's a 1 carat diamond in the middle, a ½ carat diamond on each side. The jeweler then immerses the finished ring into the ultrasonic machine. The vibrations in the water penetrate every nook and cranny, washing the ring. Finally, he puts the ring under a jet of hot steam to blast away any remaining residue. And voila! With a ring like that, who wouldn't say I do? If you have any comments about the show, or if you'd like to suggest topics